Okay, so what we're going to do in this session is introduction to big data. All you might want to dive into. Okay. Who am I? Well, I'm a lot of things. I'm currently a researcher in online persuasion classification at Hyper University. And I'm intended to start my PhD also, which will identify emotional states through video data by annotating facial expression. Okay, so I'm also a mother of two, and I have a dog named Chuck Norris. Those are my kids, and this is my dog, Chuck Norris. So why am I here? To fill in the gaps. Well, some more things that you don't know about me, that I'm always occupying filling the gaps. I'm a volunteer at Chicodes. I was a branch manager, and I'm also the course writer of data analysis with Python course. I also needed a package in Python that classifies emotions in text, and I couldn't find that one, so I created one. And I couldn't find an answer to something that I searched in Google, like how to save to a JSON file on IBM Watson, which is the cloud platform. I couldn't find an answer, so I created one myself, and I published in towards data science. So basically, I'm here to fill in the gaps. Why should you be here? Well, usually you will find out that in every session that you will have on data science, you will get an introduction to a specific tree or specific field, or here is your beautiful data, put it in a model, fit, split, and train. And what I like to do here in this session is to introduce the forest. Okay, so what we're gonna do today is provide a wider glimpse of all kinds of fields in data science. I will try to supply you an intuitive introduction to it. The theory behind it is very, very wide, okay? I'm going to provide you an understanding of what is out there. And what are we going to do today? So we're going to cover the data science pipeline. We're going to cover machine learning, a brief view of different types of machine learning. I'm going to provide you an intuitive introduction to deep learning, active learning, and reinforcement learning. I'm going to explain to you about a little bit about EDA, exploratory data analysis, a little bit about data preprocessing and social network analysis. Now, everything we're going to do in this session, okay, is not hands-on. I just want to give you the understanding of why, okay? So if anything that you don't understand the way I explain something, please stop and ask, and I will try to explain it again in a different way. So let's talk about the data science pipeline. Okay, this is a data science pipeline. So you have your data, and then you take it and you play with it, and you clean it and prepare it, and you have your model. So you take all your clean data and you put it in the model and you validate it. Okay, it's not so good. So you readjust your model and you do it again, and then you maybe deploy it and you visualize your findings. Looks pretty easy. Well, it's not always the case. Usually when you come to a research, either you have a question that you want to examine, or you have your data. So you take your data, and then you need to have a question. I mean, what are you going to do with the data? what do you want to examine? So you take your data and then you start maybe playing with it and understand the fields and what do you have in the data, and then you clean it and you explore it, and you do a little, you explore it and you pre-process it, you prepare the data for your model, and you put it inside the model and it's not so good, so you explore it again to understand what you did wrong, and then you put it again, you fix your the way you handle your data, and again you put it in the model, and it's kind of a loop, and then you have you validate your model and you tell a story. You tell you find your answer and you have actionable insights, and you share your knowledge with the world. The truth is that usually a pipeline looks a little bit more like this. You have your data in the middle, okay? You have your business understanding, your domain understanding, the field of research, okay? And then you need to understand the data. When you understand the data, it's go back and forth with the domain understanding. So you understand the data and you need to prepare it to the model, okay? And then you model it and it's not so good, so you need to re-prepare the data, and again, it's a loop, and then you evaluate it, and maybe the evaluation contributes to the domain understanding. And after all of this, you deploy it, and it's a loop. You do it again and again and again, and the data is in the center. So this brings us to the model, to the machine learning model. Well, a classical machine learning model, okay, the data itself will look something like that. So you have your feature metrics, okay, so you have all kinds of fields. Like, for example, you have a transaction, so you have the customer and its ID, maybe the credit card number, the type of the credit card number, the time of the transaction, and then you have a target vector, okay? So the target vector, it's maybe if, I don't know, maybe if you returned the product or you didn't, maybe it's a fraud transaction in the credit card fraud or isn't. The target vector, it's the labels, okay? So this brings us to the types of machine learning that we have. Okay, so you have the supervised learning. This is what I introduced. And here you have regression or classification, okay? In this specific slide, you can see all kinds of fields of research that you use it for. Okay, so you have your supervised machine learning, and you have your classification, like image classification, customer retention. You have your regression, like weather forecasting. You have your unsupervised machine learning, which means that you don't have the labels. Okay, you just have the data of the transaction. You don't have any other information, whether it was fraud, whether he returned the product or he didn't. So here you have clustering, like targeted marketing, like ads that target you for things that you might want to buy. You have dimensionality reduction, like big data visualization. Okay, this is also dimensional reduction. It's like PCA. And you have your reinforcement learning. And this is something else that we're going to talk about this session. Like you have real-time decisions or robot navigation. This is the fields of study of machine learning, okay? Beside supervised and unsupervised, we also have something in the middle. It's called semi-supervised learning, okay? Where you have partially labeled data, okay? It means that maybe about 10% of your data has labeled. Not everything, only 10%. And also we want to talk about it a little bit later, and I will explain a little bit more the intuition, how it's going, how it's working. Okay, so here in this slide, we have machine learning and all types of algorithms that's connected to them. Again, I'm not going to enter the mathematics and the theory about each one of them, but as you can see, some of those name of the algorithms you probably know from
יש לי שאלה.
Yeah.
Sorry, I have a question. Are we going to get the slides at the end? Because that
Yes,
is a lot
absolutely.
of information on every slide.
I know, and everything I'm saying, okay, maybe a little bit written a little bit better. You already have in the file everything I'm saying. Every slide you have with information of what I'm about to say about it as a PDF file in your shared folder. I put it there last night.
Okay, thank you so much.
Sure. I know it's a lot of information, and as Andrea and G say, don't worry about it. Here you have your machine learning algorithms. So you have your classification, and you have naive Bayes, which you probably know from statistics that you learn. I don't know in which degree you had, but everybody learned it. And you have your regression, also statistics. So it's pretty much statistics. Everything here is statistics inside mathematics. And this is, you will have this slide. So everything you want to learn more about specific algorithm, how to apply it, everything, you're more than welcome to Google it. I'm sure that everything has a tutorial, and if it doesn't have a good tutorial, I urge you to create one. So let's go into the deep. Do you know who they are? Those lovely gentlemen. What are their names? How are they connected to deep learning? You can answer.
Yeah, open your speakers and you can answer. Open your video, feel free. Like it's an, I don't know, frontal lecture. Feel free to be
a part.
Comfortable.
And don't pick in your PDF files. Okay, so the person you're viewing here, okay, are the founding fathers of deep learning. Okay, you have from the left, you have Walter Pitts, and you have Warren Macaulay. Those two created together what it calls artificial neural network, ANN. Okay, now I also thought so, but you have this. I thought that the people that invented the neural network didn't have any idea how a human brain works like, and you know I thought they were mathematicians. So they created a computational model of the brain. But those two had a pretty good knowledge of the human brain and how it works. They were neuroscientists, okay? And on the right, you have Frank Rosenblatt, and he invented the perceptron. And the perceptron is the first computational computer, okay? That it was the first computer that learned new skills by trial and error. Okay, so those three are three of the founding fathers of the deep learning field. So what is a neural network and how does it work? Okay, so this is a neural network. Okay, so you have your input, and you have the input layer, and you have the hidden layer, and you have the output layer. Let's assume that your data is a picture. So your picture is like 5 by 5 pixels. And what you do in order to put it inside the model, you need to flatten it into a vector. So you take your model and you take your picture and you put it, you turn it into a vector. So you have this long line of 25 pixels, and each one of the pixel is an input, okay? So the first pixel goes to the input, and then the first input, and then it goes to every one neurons of the hidden layer, okay? And it's like a black box, and then it goes out the output, okay? All the inputs goes in, each one of the inputs go to every piece of the hidden layer, and then it go out on the output layers, okay? Now, the black box, the difference between deep learning and classic machine learning is to take the algorithm one step further from the programmer, okay, and one step towards AI, okay. So each hidden layer, each black box takes the output one step closer to AI and one step farther from the programmer. Okay, let's assume that your specific model, okay, this is pretty much how it works. Okay, it looks like a company. Okay, so you have your picture. Okay, you go to the company of the neural network. You knock on the door. You give the man on the door is the picture. Okay, and then the man on the door breaks the picture to a little small pixels. Okay, and you have your low-level employees. Each one of the employees get a pixel. Okay, and you have a pixel with a little bit of black and a little bit of white and all sorts of colors. Okay, and then you go to their team leader. Okay, so you have your team leader that is in charge of the curved line, and the one that is in charge of the straight lines, and one that is in charge of the edges, and one that is in charge of the curves. And each one of the low-level employees goes, it's not this network scheme, it's a little bit, what I'm explaining, it's a little bit different, okay? But if every one of the low-level employees goes to each one of the team leaders, okay? So each one of the team leaders looks at all of the pixels, okay? And then he decides, okay, this fits for me for those three builds for me a straight line. And those three pixels give me an edge. And those four give me a curve, and so on. And then they have all this, they have their curves and the edges and the straight lines, okay? And then they go to their managers, okay? Again, so let's assume that the picture is of a dog. So then you have the one that is in charge of the right eye, and the one that is in charge of the left eye, and the one that is in charge of the tail, or the paw, or the ear. So each one of the team manager, okay, goes to his supervisor and show them the curves and the edges and the straight lines, and the supervisor of the eye, okay, so I need an edge and I need a curve, and I need maybe a small round thing for the iris, and then okay, I have those, and I'm pretty sure, I'm 70% sure that this is the right eye, and so on for every one of those. Now the 70% is kind of important because this is logistic regression, and logistic regression work on weighted sum. So everything under 50% is a no. Everything about 70%, it's a yes. So so then you have your right eye and your black eye, your right eye and your left eye and your snout and so on. And then all of those are going to their big boss, and they say to him, okay, I have this and this and this, and the big boss thinks about it, and then she's okay. So she's saying like, yes, I'm pretty sure, about 80% sure that this is a dog. Okay, so there is another.
Can you repeat it? It's logistic regression is 50-50? It's supposed to, it's a yes/no question, or?
Logistic regression works on weighted sum. So inside of those layers, what they have, it's like everything. It's like everything under 50% is a no, okay, and everything about 70% is a yes. In the middle, you need to work on your data.
Okay, thank you.
Sure. So you have your, this is you see, you have your pictures, your training a picture, okay? You have your input, which is a pixel of a dog picture. And then you have your first layer, okay? So you have your curves and your straights and your edges, okay? And then you go to the supervisors. You have a supervisor for the tails and the paw and the nose and the legs. And then you have your top layer, which is the top layers that which classifies your data, whether it's sure it's a dog or it's not. Okay, so it's 90% sure it's a dog. And then you can see here, you have a face of a pit bull. So you have like the left eye and the right eye and the snout and the mouth. And here is another picture of a dog. So you take the picture of his nose, and you have the top of his nose and the right part of his nose and the left part of his nose, and then you train your model. And what it does, and what sometimes it does, it predicts that your cat is actually a dog. Okay, so this was this session. Okay, we learn a little bit intuitively about what is deep learning and how it's working, what the black box looks like, and the founding fathers. Okay, now we talked about labeling. I don't know if any of you ever labeled data before. It's exhausting. Okay, it's very, very hard job. So if your company paying somebody to label your data, they probably worth every penny, and you should pay them more. And well, labeling costs money, a lot of money, a lot of time, and why not do it a little bit smarter? Okay, so you have your passive machine learning. Okay, this is the classical supervised machine learning, where you have your unlabeled data, you give it to the man, he puts labels on it, it classifies picture as a dog or as a cat, it classifies your text as offensive or not offensive, or whatever you wish, okay? And then it gives you your labeled data, and you put it inside your model, and then you train your classifier. As I said, it costs a lot of money and a lot of time to do all of this process. So what are we going to do about it? Well, you can do deep learning. Okay, you can do unsupervised learning, you can do clustering, you can do semi-supervised, and what you do in semi-supervised learning is you label maybe 10% of your data, and what you do is you train your model on that 10%, okay? And then you predict for the rest of the 90% of your unlabeled data. This process called pseudo labeling. So you have your pseudo labeling of your data. Now this brings us to the new subject of active machine learning. Okay, so you have your unlabeled data. Okay, you put it in the active learning, and here you have about 10% of your data labeled. Okay, so what you do is, again, the semi-supervised learning. You train your model on your 10%, and then you predict the labels of the rest of the 90. And now you ask the model, please bring us, please label things that you're confident about your, please label pictures that you're confident for more than 90% as a dog, label them as a dog. What you don't sure about, what you don't have low confidence of, show me those data, and this data that you don't have confidence of, I will give it back to the man to label those data points. Okay, those those inputs. Okay, so what this is called smart labeling and active learning. So you have your 10% of the data labeled, and then you predict the labels of the rest of the 90%. The labels that the computer is not sure about, you give them to a man to human label them. Okay, and then you repeat the process again and again, and until you perfect the number of items you have labeled, and the rest of the predicted data points that you have a very good confidence about their labels. And this is an example. So you have your active learner, the robot. You give them a picture of a cat. Please identify a picture of a cat like this one, and then he asks you about pictures that he's not sure about. This is the field of active learning. Very, very interesting. So what are you going to do when there is no data points, there you don't have data, and you don't have labels? This is the field of reinforcement learning. Okay, in reinforcement learning, you don't have data. All you have is the environment and the agent and its rules. Let's assume that what you're going to do is predict your stock market. Okay, so you have the stock market, which is the environment, and the agent is your portfolio. So you have your action. Okay, you can buy stocks and you sell stocks, and you have your rewards. So you did a good job. So your stock portfolio going up. You didn't do a good job. Okay. So your punishment is that your stocks are going down. Okay, so this is kind of a loop that the agent learn how to act. Okay. Another field of reinforcement learning is games. So you have your agent and you have your environment, and there is a fire and there is a bucket of water. Okay, and then he goes to the fire and he gets burned. Ouch! It costs him 50 points. So he learns that the fire is bad, and next time he needs to avoid it. Now, how far can it go? Have you ever learned about DeepMind, AlphaGo, AlphaGo Zero? Okay.
Go is the
Do you hear it?
It is one of the simplest.
Yeah, it's okay. Thank you, Dina.
Okay.
The long-standing challenge of artificial intelligence. Everything you've ever tried in AI falls over when you try the game. The number of possible configurations of the board is more than the number of atoms in the universe. Found a way to learn like Go. So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lisa Dobbin.
Perhaps like no other is about to get underway in South Korea.
They said always to go where Roger Federer is, and it's just the very thought of a machine playing human is inherently intriguing. The place is a madhouse. Welcome to the DeepMind Challenge All Worlds. Watch, can we still find AlphaGo's weakness? Whoa. Is there in fact a weakness? Game kind of turned on its axis. Well, nice. Nice, no cost that nice. It's developing into a very, very dangerous fight. Hold the bomb. Green has left the room. It's about to cry. I think this sounds like wrong. Yeah, it's man. Tension's got lots of weird. These ideas that are driving AlphaGo are going to drive our future. This is it, folks.
This full movie was available on Netflix. I think it's not there now. But this one was AlphaGo, and a little bit of spoiler. AlphaGo won against the world champion. It was kind of diplomatically problematic after they won in China. USA won in China. So after this, they created AlphaGo Zero, and I'm gonna show you. Okay. So next slide. This is AlphaGo Zero. I'm gonna try to put a citation on this one. No, I cannot put here.
AlphaGo Zero is the strongest Go program in the world. It outperformed all previous versions of AlphaGo. Specifically, it defeated the version of AlphaGo that won against the world champion Isidol, and it beat that version of AlphaGo by 100 games to 0. So all previous versions of AlphaGo started by training on human data. And they were told, well, in this position, the human expert played this particular. In this other position, the human expert played here. AlphaGo Zero doesn't use any human data whatsoever. Instead, what it has to do is learn for itself, completely from self-play. So the reason that playing against itself enables it to do so much better than using strong human data is that, first of all, AlphaGo always has an opponent of just the right level. So it starts off extremely naive. It starts off with completely random play. And yet, at every step of the learning process, it has an opponent, sparring partner, if you like, that is exactly calibrated to its current level of performance. And to begin with, these players are very, very weak. But over time, they become progressively stronger and stronger and stronger. People tend to assume that machine learning is all about big data and massive amounts of computation. But actually, what we saw in AlphaGo Zero is that algorithms matter much more than either compute or data availability. In fact, in AlphaGo Zero, we used more than an order of magnitude less computation than we used in previous versions of AlphaGo. And yet it was able to perform at a much higher level due to using much more principled algorithms than we had before. I think I can speak for the team by saying that we were all pleasantly surprised by just how far it went, that eventually it was able to surpass all of our expectations. It was able to actually climb up the ratings until after around 40 days, we found that it had actually defeated all previous versions of AlphaGo to become the strongest Go program in the world. And this is all for a system that's been trained completely from scratch, starting from random behavior and progressing from first principles to really discover tabula rasa, how to play the game of Go.
I have a
So
question about that video.
Sure.
I think his main point there was that algorithms matter more than either compute or data. And I think that generally from what I've heard on the field, the opposite is usually the common phrase. Normally people say, we've discovered that it doesn't really matter exactly which algorithm you use. If you have lots and lots of data and you have enough compute, your algorithms will eventually converge more or less to the same behavior. So I'm confused at how these two beliefs match with each other. If you have any input on that.
I think that this is an excellent question. Okay, I agree with you that what he's saying is very, very interesting, and I do know that you have like a package. I don't know if all of you know Yam, but he created the Unga Bunga, and this is like a package that uses a lot of computing power. And what he does is like, okay, let's take let's put inside all of the data and use all the algorithms and all the weights and all. Let's try everything, okay, and let's see what goes out on the other side, okay. So I know and familiar with what you're saying, okay, but what he's saying also here, I don't know if it's colliding. What using all the computing power and all of the data, and on the other field, on the other side is a self-learner that understands the world. So if you're having usually robotics, okay, you have all the kind of AI and robotics and navigation of robots, it usually works on reinforcement learning. The data, as it said on AlphaGo, is restricting because it doesn't learn from things that nobody ever tried before. What do you think? Anybody else want to answer it, maybe? To join the discussion? It's an interesting discussion.
I think that maybe what he's actually saying I mean, first of all, there have been works showing that usually it doesn't matter exactly how you tweak, it doesn't matter as much how exactly you tweak the data, but the algorithm with the most data wins. But it doesn't mean that you can't sometimes find like something that's, I don't know if even it should be called truly revolutionary, because he just started with, let's not give him any predefined data and just let the algorithm roll with it and learn the world pretty much like, I don't know, maybe a human child would learn how to play with his friends, and eventually they would all become master players together.
Yeah.
So maybe the concept here is that if we really want the algorithm to learn to do something very like innovative, maybe what we're usually trying to get with having the most classified data is that we're trying to reach human performance levels. Because usually the tasks we're trying to solve are tasks that we think humans do very well, or fairly well, and we want algorithms to match that. So any classified or input data we can generate for them is human generated. And here they didn't give them any human generated knowledge and let the system really learn at random. So it gives it the freedom to find like truly innovative solutions.
Right. So maybe it's actually the difference between unsupervised and reinforcement, when you maybe have data or you have unlabeled data, or you don't have any data at all. And deep learning is and all kind of computing power and data is another field of labeled algorithms. Maybe this is the difference also. Between those two approach for data. But a lot of data points sometimes can sometimes also leads maybe to overfitting, and you need to sometimes maybe more generalize your model. So again, it's a very, very interesting question. And
I think it's not only having lots of data, but also having the right data for your question.
Yeah. So we have right now we viewed data science pipeline. Okay, so you have your definition of a problem, and you analyze your data and you prepare your data, and then you evaluate your algorithms, and you improve your result, and then you present your result. I think that what we're going to do now is maybe do a 5-minute break before our next subject, okay, for this session. Next session, it will be something else. So what I'm going to do now is share another screen with you. Wait. You see the screen? Okay, I'm gonna put a 5-minute timer so all of you can go and stretch and fill your water bottles and refresh or whatever else you need, okay? לטובת כל מי שקמה ורוצה לחזור, לשבת ולהצטרף אלינו ולפתוח מצלמה, אנחנו עוד דקה חוזרות. כן, מוזמנות לחזור ולפתוח מצלמה. כולן חזרו, אפשר אני ממשיכה. Okay, so we're back and we're here. Okay, you have your data science pipeline, and now what? Now we begin at the beginning. This is a quote from Alice in Wonderland, and we will begin at the beginning. What is the beginning? It's the EDA, data exploration, exploratory data analysis. So why do we do EDA? Well, the data in the real world is dirty. You need to understand your data so you know how to clean it, how to spot the missing data, outliers, human errors, and you need to understand how the data looks like. How which variables you have and how they connect to one another and how they correlate between themselves and the target. So why do we need it for? So data in the real world, as I said, is very, very dirty. So there is an expression called garbage in, garbage out. If you put garbage in your model, this is what you will receive on the other side of it. Your analysis is only as good as your data. So why do we do it? And what does it do? You understand your variables and the relationship between them, and it helps you clean the data set. So how you do it? The methods are univariate visualization. It provides a summary statistics for each field in your data set. Okay, like the mean and the average and the maximum and the minimum. And you have the bivariate visualization, where you plot two variables and you view the connection between them. Between them and the target, and you have your multivariate visualization, where you plot and understand how two variables in your dataset connects. And then you have your dimensionality reduction. Maybe you heard about PCA. What it does, it actually, like if you have a 3D dimensional data, you can visualize it, maybe imagine it like a basketball ball in a 3D field. And then what the dimensionality reduction does is actually the shadow of the basketball. So you have the basketball, and what you put inside your model, it's only the representation, only the shadow of the basketball. And then you know it's the shadow of the basketball, and then you understand which features more correlate and affect the classification of the target. So you have use plots for EDA. So you have histogram that you want to check the distribution of a specific variable. You have scatter plots if you want to examine the connection between two features, between two variables. You have maps if you have you can plot on maps if you have geographical data. You can show you the distribution of your data on a regional or a global map. You have a feature correlation plot, which is a heat map, to see how two variables are connected. If two variables are the same, why you need to use them both. For example, if you have a zip code and a place, why you need both features. Again, as I said before, data processing, the computing power costs money. So the more data you have, the more costs you have. The model will take longer to run. You will need more computing power. Everything costs. And you have time series plots if you have to identify trends, and seasonality depends on in time-dependent data.
I really wish there were pictures for all of these kind of plots.
Sure, and you will have them, and we will do it in the next session. And you will also have a link, a QR code for an awesome guide to how to do all of those.
Thank you.
Sure. Any other questions so far? So far, so good. Okay, so now we're reaching to data pre-processing. Okay, so you have your data, and you have your missing values and your outliers, and you found out some human errors where they wrote I don't know, maybe something with a typo, or classifying one thing they typed, not classified, but I don't know, they wrote male as 0 and women as 1 is the gender and as the sex in the data. Then you need to put it other way around in the data, or you need to change from they wrote F for female and 1 for man, and you need to put it the same type of labeling of this specific variable, and you need to change it. So we reached the cleaning part, the pre-processing part. Okay, so how do you do it? Let's assume that your data is the housing prices. So let's remove all the missing data. But if a house is missing a pool and you remove this line, would it just tilt your distribution? You just keep on your data all the houses with a pool. So it might tilt your distribution and dismorph your data. So what do we clean? We clean missing and outliers and features. As I said before, computer power costs. And if you have two features that are pretty much the same, why do you need them both? If you have features that don't correlate to the target, so they don't give anything to the prediction of your model. So why do you need them? It's just more memory space and more things to compute, more space in your computer, in your memory. So this is what we clean. How do we clean? What is wrong clean do? It creates bias in your data. It can tilt your distribution, and it can dismorph your data. The right cleaning can help you reduce costs reduce process time, and reduce overfitting. Okay, when you overfitting is you give a lot of data points into your model, and then if something is not in your data and it's different from the data that you have, your model will be won't predict it the right way, because your model is not generalized enough. I won't get into the how to this session, okay, but we will cover this today on the next session. Okay, so let's talk about, we did the data processing. Okay, now let's talk about feature. We talked about that some features maybe not correlate with the target and not predict them, and not predict the target, so maybe we don't need them all. And some features correlate one another, have a high correlation with one another, which means that they are practically the same, so do we really need them all? And this brings us to the next session of features. Should we really address all the features the same and put them inside our model in the same kind of way? Do every feature contribute to the prediction the same way? This brings us to feature engineering.
Dina?
Okay. Yeah.
Features are predictors, basically?
Features are the variables in your metrics. Okay. So you have a feature is like you have a lot of transaction. Okay, each transaction is a row of an input. Okay, and then your feature is like the date. So it's the dates of all of the features, all of the inputs. And you have the type of credit card, so it's the type of credit card. This is a feature, okay? So you have it in every row of your data.
Okay, thank you.
Okay, so let's say that what we're going to do now, it's predict the cost of an health insurance, okay? So when maybe you are young, you're going to your doctor maybe once a year. In your 20s, and then you reach your 60s, and then you maybe go to your doctor once every 6 months, and then you reach your 80s, and then you maybe meet your doctor once a week. Okay, so your age is a feature, but as you can see, it's not linear. You don't, it doesn't have like every year. It's not you coming for your doctor one more. It's not linear. It's more like exponential, and the age will probably need to be like age square, this feature. Okay, so you have your age feature, and you have your obesity and the danger of and the smoking. Okay, those are two features of the health insurance. Now, they can come separately, okay? Each one of them has their own health hazard. People that suffer from obesity has health issues, and people who smoke also have health issues. But people that both suffer from obesity and smoke suffer from more health insurance. And their health insurance equation will probably skyrocket. So your health insurance equation will probably look something like this. So you have your smoking and your obesity, and you have your age square. Okay? So this brings us to feature and influence. Why influence? Well, my research deals with the online persuasion classification, and it also deals with influence. Influence is very interesting in how what makes people decide stuff and makes them behave one way or another. So we have features and influence. Okay, so we have this table from an article that written a research that you have, you see it downstairs. What they did in this research is they took, their data was Wikipedia talk pages, okay? And what they used is something that's called author's trace. So author's trace is like the information about the person itself. It's age, it's gender, it's political party. And what they did is they classify the topics of the pages, like for example, abortion, Catholic Church, Israel, Michael Jackson, and then they saw how much it is associated with a specific author's trace. A specific demographic feature of the author, of the writer. So you have abortion is very associated with gender, and you have the Catholic Church that is very a high association with religion, and you have George Bush, which has a high association with politics, and Michael Jackson, that most of the authors, the most significant feature of people who wrote about Michael Jackson was the age. Okay, so what they did, they want to see how much people influence. Okay, where young people, you want to see them if they have a high influence or they're not influenceable at all. And you see the binary features by influence, yes, no, over here, the breakdown of the feature. And then what they saw, what they did is connect them. They took the gender and the political party, and they plotted the breakdown of the influencer and non-influencer in the training data. Based on the binary combination of feature and gender of political party. So you have your male Republican and male Democrat and male female Republican and female Democrat. Okay, and what you see here is actually that female that are Democrats are less influencer than female Republican, for example. Even though that women are 53% more likely to be a Democrat. So this what you see here is when you combine two features, this is feature engineering. Okay, this is the connection between feature engineering and influence. Now, when you're combining features together, you need to be aware of something that's called Simpson paradox. Okay, Simpson paradox, okay, you can see here you have all kind of trends in several different groups, but when you combine them, the trend disappear or reverse, okay? So you have all of the trends in the features that going up, and then when you combine all of the features, the trend is the trend is going down. Okay, this is called Simpson paradox, and this is something to take into account when you combine features. Okay, now let's go back to features and influence.
Dina, sorry, can I ask a question?
Sure.
So the idea is that you need to, if you want to really get the real trends, you need to have subgroups. That's the paradox, right? Or the other way around?
The paradox is that you have some groups, okay? You have subgroups, all kind of subgroups in your data. But then when you combine all of those into one feature, okay? So you have your subgroups. So you have, let's say you have the political party is Democrats, and you have Hispanics and Caucasian and Caucasian male and Caucasian women and all kind of those subgroups, okay? And then you combine them, and it's a completely different trends.
So if you want to really understand your data, you need to inspect your subgroups, because in the total, you are missing the trends of the subgroups.
Sometimes, but sometimes the data is not really divided into subgroups.
Yeah, you need to create a division, or you need to understand the division.
Yeah, exactly.
Okay.
Like before, you had a subgroup of, you have a subgroup that is, you have, your data is labeled, it's not labeled, okay? You have your feature of your political party and the gender and all kind of other features, okay? And then when you look only on Republicans, it's one trend, and you look only on women, it's another trend. But if you check the subgroup of Republican women, it's another trend. If you check up your feature of Republican male or Democrat male, it's another trend that you're viewing in your data.
Okay, thank you.
Sure. So let's go back to influence. Anybody knows what those words mean? Homophilia, social proof, echo chambers, filter bubbles. Those are terms that connect to influence. Okay, so you have your homophilia. Homophilia is a tendency of a person to resemble is social group, okay? So you are similar to your friends. You have the same political party as your friends in Facebook, okay? It also connects to social proof, which is a term that connects to Cialdini's 6 weapons of influence. Okay, if you want to reach somebody, you need to connect with them on the level of, this is kind of connected to also targeted marketing. Okay, so you have the same ads as your friend, and you will view a filter bubble also connects to filter bubble is an algorithm. It also connects to the same thing, okay, that you're viewing the same kind of a data as your friend. And you will view, like if most of your friends are Democrats, you will see more posts that connected to this side of the political map. And echo chambers deals with the fact that like in a social group, for example, you have the Democrats and the Republicans, and those two are two social groups. And the information that goes inside these echo chambers are only informations that are resemble and reinforce the information that also already exists and the beliefs and the values of the specific group that's inside the echo chambers. For example, you will see for the Democrats, you will see their information against Donald Trump, and for the Republicans, you will see make America great again and all kind of stuff. Okay, so what I did in the, I'm taking you back to the article about, to the research about author's trace on Wikipedia talk pages, is what they did is check the majority of the influencer, if an influencer is the majority or not the majority in a discussion. And what they saw is actually that when somebody is in the majority is more likely to be an influencer, which brings us back to all of the social proof and the echo chambers from before, and the homophilia. Okay, when there is a lot of people that resemble to you, you will agree with them. So this is something that is very interesting and very interesting social phenomena. Okay, and this is one way to examine the topic of influence. Okay, through review influence accordingly to the features. But another field of influence research is through social network analysis. Okay, so we're going to talk about an article that examines social influence using methods from social network analysis. What they did specifically is identify types of influencers. Okay, here you have a nice visualization of their data. This is an article from last year. Okay. And what they did, their data was 3 days surrounding the trials of a Brazilian president called Lula. He had a corruption trial, very similar to what's going on here. So this is what you see is the visualization. They used a program that's called Gephi. And you see here in different colors, pro and against President Lula. And they identified 4 types of influencers using a matrix of participation, visibility, and political position. Okay, if they have and don't have a political position.
Can I ask a question?
Sure.
I did not exactly understand if we are influencers. We're discussing. I'm not exactly sure if we're still talking about feature engineering. Is like influencers a data science term, or we're just looking at an example of an interesting study that examined social influence?
Okay, so
I'm trying to understand in which realm we are.
Okay, so before that we were in feature engineering, and we talked about an interesting article and an example of an article dealing with social influence and how they use feature engineering to examine feature engineering. And now we're moving to the next subject, which is social network analysis, but we're keeping the subject of influencers.
Okay, so our problem domain is we are looking at social influence,
yes.
And we are
examining. Right now we're checking it.
Talking about feature engineering, and now we're looking at social network analysis, which is another kind of algorithm that we're applying to the same domain.
Yes.
Right? Okay. Thank you.
Sure.
And how are we defining social influence? How do we measure it? How are we measuring social influence?
So we're what we did is there is all kind of way to measure it. You can see participation. Okay, we will talk about it here on how they measure it. Here they measure participation by the number of how much the users are active. Okay, and they measure participation on how much people share. If you have like a user, if we're talking about Twitter, so you have this user, and a lot of people are retweeting his tweets, or a lot of people are mentioning the same user. So this one is an influencer, and the one that tweets a lot and talk about and has a lot of activity is also an influencer. And I will get to that. Okay, thank you for all the questions. They're very, very, very good. So we are now talking about measuring influence through a social network and social network analysis. Now let's talk about what is a social network. Okay, so you have in a social network, you have your points and you have your lines. Okay, so if we're talking about people, we have followers or friendships or kins. If we're talking about companies, maybe you're talking about acquire or trade or a chain of supply. If you're talking about disease, actually it's supposed to be sick people. So you have your chain of infection. If you have web pages, their lines are the links. If you have articles, then you have citation and maybe the writers. And those points and lines have formal names that vary from different disciplines. So you have your vertex and edge and maybe arch in math, and you have your nodes and edges in computer science. This is what we are using, and you have your actors and ties and relationships in sociology. Okay, so let's go back to our research that we are dealing here, and what are metrics they used. So you have your modularity. It measures how many different groups you have, for how many groups you can divide the data that you are looking for, your data points, how many groups. How many clusters, how many communities. You have your in degree. We're talking, this data specifically is Twitter. So you have two forms of networks. You have a directed network like Twitter. In Twitter, you can follow somebody, okay, and it cannot follow you back, okay. So you follow him, but he doesn't follow you. You can retweet something to share, okay. So it's not mutual. In Facebook, for example, if I'm your friend, you're my friend. So this is an undirected network. Another form of directed network is maybe a family tree. So he is my grandfather, but I'm not his grandfather. I'm his granddaughter. Okay, so if we're talking about it as a family tree of kin, so yes, we are related. But if we're talking about it like in an hierarchical way, so it's undirected. So it's directed. So we have your in degree, okay? In degree and out degree. Let's talk for a minute about degrees. So in an undirected network, degrees are the number of lines, okay? The number of edges that connected that connects to a dot. So in degree, in a directed network, it's the number of degrees that goes into a node, okay? And an out degree, it's the number of lines that go out from a node, okay? So you have in degree, the number of mentions and retweets received by a user. So it indicates on visibility. So you have a user, okay? Let's say your user is Donald Trump, and the number of times somebody uses an @ sign at Donald Trump, okay? The number of times people mentioned him. And out degree, okay, it's the number of users that somebody retweeted or mentioned in a given network. That shows participation, which means the number of time people were active on the network, okay? And what they found out, and they found out that there are 4 types, they identified 4 types of influencer. You have users with a clear political position. You have opinion leaders with an I in degree, which means a lot of leaders, a lot of mentions and retweets. You have activists, which is with a high out degree, and large number of users that somebody retweets and mentions in a given network. Okay, they are very, very active. And opinion leaders have a lot of visibility. And you have users without a clear political position. You have informational influencer that has an high in degree, usually news outlets. Okay, for example, I don't know, Fox News and all kind of stuff. And you have news clippers, which has all kinds of, also have an high out degree. A lot of people that like bots, sometimes they are bots, and somebody that that advertises a lot of stuff and a lot of information. And with those without a clear political position, I'm taking you back to the echo chambers from before. What happened here is that usually each one of the conversation takes those into his echo chamber, and then to reinforce information and beliefs that already exist in the echo chambers. Social network analysis can be also applied to security. Okay, here you have an article that talks about it. So let's say you have a network of computers and you want to spot anomalies in the network. For example, a new type of camera all of a sudden joined your network, so you want to know about it if the network changes. A new type of computer, on a new user. Okay, so the social network analysis can be also applied to security, and it can also be applied on ecological systems, and it's not only social.
So just to make sure I understand, if I got that part correctly, they're doing social network analysis. They treat the social network as a kind of graph. Then they developed some algorithms for this graph. And then they're saying, okay, so let's use this social network analysis everywhere else.
It's a social network analysis is a name when you're using it in data science, but in other fields it's graph theory, and I don't know how many which other names they have. It's not limited. It didn't start from a social network. It's graph theory. For example, it goes way back for I think that the 18th century or so, when there was a cholera outbreak in London, and they wanted to examine which one of the where is the initial start of this outbreak, and to predict, to understand which one of the whales were infected. So it's connected to social and people and the relationship, but it's not limited. It can, as I said, it can predict and understand, and not predict, it can understand the way a disease spread. It can understand the food chain. It can understand the network of computer, network of people, connection between different countries, between different companies, between for example, this article, which other articles they're quoting, and those articles which quotation they have, and so on and so on and so on. So it's building a network, a graph, or a web of connection between similar, I don't know, I think similar items, for example, between articles, between authors, between people that got infected from a disease, between people in a specific discussion, like this political discussion on Wikipedia talk pages, a specific discussion connected to President Lula's trial, and so on.
So basically like, you're saying the data scientist term for looking up, if I wanted to see how the data science world addresses a problem that could the Corman book of algorithms first year would treat it as a graph problem, then I should be looking for the SNA, for the social network analysis parts
Yes,
of the data science world.
Yeah.
Okay.
And later you can remind me, and I will share with you an excellent Israeli podcast in Hebrew about this specific subject if you're interested.
Okay, cool, thank you.
בדיוק חשבתי על זה עכשיו, אבל... sorry, I just thought about this podcast a second before you said that.
Yeah, Shapiro.
Netflix, right?
Yes, Netflix, exactly.
Yes, it's really good.
Yeah.
Okay, great, thank you.
Sure. So, what are those have in common? How are they connected to social network analysis? And how can it contribute for your awesomeness in every conversation? Anyone? Come on, and the man in the middle you probably recognize.
The man in the middle is Kevin Bacon, right?
Yeah. Any mathematician in the audience? Who is the man on
the other one must be Erdesh.
Yeah. And any
and
psychologist?
Who's the third one?
The third one, psychology. Psychology. No, okay. The man on the right is Stanley Milgram. Okay? And how are they connected?
I didn't know there was a degree of Milgram. I was not aware.
Exactly. Okay, so
I don't think that would be a great honor given what he's famous for.
I don't remember what are you talking about?
Well, the 6 degrees of Kevin Bacon is because it's kind of an honor to have been in a film with, you know, Kevin Bacon, or to have written a paper with Paul Erdesh. Yeah. But Stanley Milgram is mostly famous for his prison experiments and for showing how you could deteriorate a society. So I'm a little bit surprised that there is a Milgram number for psychologists.
So the Stanley Milgram is also famous for the small world experiment, okay? And what the small world experiment, what it did is, I think it was in the 60s, and what he did is the experiment was to transform a letter from one side of a country in the, I don't remember all the details, but it's to send transact a letter from one side in the United States to another person in another side of the country. I see that you already have the link for the podcast, for the podcast. So what he did in this experiment is to move the letter from one side of the United States to another side, and you need to, like, you have a letter and then you send it to another person, and this person put it in another envelope and you change it to another person until you reach the destinated man. So in this field was the average degree of 6 people between the first one that got the letter until the last one got the letter. Okay, this was the small world experiment. So this brings us to another term that's called 6 degrees separation. So it means between you and Bill Gates, there is the average of 6% between you and him. So if you maybe want to send a message, so you send a message to your friend and he sends it to his friend and the 6th person in this will be in this transaction of letters will have probably be a friend of Bill Gates, and it could transmit your letter to Bill Gates. I just want to say that now in social media today, it's probably even less. An article from 2010 of Twitter measured 4 degrees of separation. So I think that nowadays in Twitter, it's probably even less. So this is this 6 degree of separation is connected to also to the small world experiment of Stanley Milgram. Okay, and this brings us to the 6 degrees of Kevin Bacon, the Oracle of Bacon. You will have the links. Okay, I think 2 years ago I checked about Dubigal and it was like 3. And you have Erdős number project, which is what is the separation degree between you and somebody who wrote an article with Erdős. Okay, supposed to have some publication to use this Erdős number, but this is very cool and very nice. And you will have also the access to the links. So another thing that I want to give to you is a present. Okay, this is a cool website, a cool app. It's called Socrates Insights. Okay, what it does is you search your article. Okay, let's say you want to build usually when you're coming to the data science project, so you have your field, you have your data, and then you go and research what is the most innovative research on the field of domain and your study, and what you want to do, and see what kind of algorithms they used. And then you come to this website, and you're supposed to log in, and you can ask for them for a demo. This is an Israeli organization, and I also contact them about it for a permission to use their, to show their tool. So you come here and you search your articles, and then it can offer you all kind of related authors that correlates with what you are looking for. Okay, so you can see the notes, and you can see where they're from, which country, and how are they connected. So you have a size by document count, and the color is, I don't know if you can see this. You can see my pointer or not? You can see my, okay, so you have your, okay. Okay, so you have the color by recent region, where have been the writing from the last 2 or 3 years. And you can see this type of view. This is the author's type. Before there was the documents, okay? And now you have the author's graph, okay? So what you can do here, and you can change by the size of the score, okay? So you can see how much a specific author is important to the field, okay? How much citation he has, okay? This brings you a different kind of visualization to see which one. You see the bigger nodes are the most important authors of what you were looking for. Okay, again, so you can see where they're from North America, and you can view it this way. And then you can go and click on one of those authors, and then you can see their profile, and you can see their institute and the research interest, and you can see all kind of terms, and you can see the articles and co-authors, and you can view the full profile of the author. Okay, and here you can enter the full overview of the author's profile, and you can see with who you wrote with, and you can see the publication, and you can see the publication per year, and you can see a term graph, and you will reach a term graph shortly. Okay, and now we have the similarity. Okay, so you have your author, and this is who you want to focus in, because you want to apply his algorithms and his novel approach for your domain. and you want to search somebody that is similar to him. Okay, so you can do a size by similarity, and to find out which authors are more connected and more similar to the one that you're looking for. Okay, now sometimes when you're looking to research something and you maxed out on the terms in Google Scholar and you're searching for information and you have no idea which term else to use on your search. I don't know if you encounter this problem. I think it's connected to the domain and the field of research, but sometimes you use all the research terms all the queries that you thought about them and you maxed out, and you're not coming out with new result, and you want to view some new result you didn't saw before. So no problem. They supply a term graph. And what you're viewing here is terms that are connected to the terms to the queries and the terms that you were looking for. Okay, this is an awesome graph visualization. And here you can see the terms, and you can see, for example, that you search for 3D implement state-of-the-art, and you can see that state-of-the-art is connected to innovation. And here you can also see novel approach, state-of-the-art, novel technology, all kinds of terms that are connected to those. And you can see that laser, they have more terms that are similar to the terms that you were using for, okay? Awesome, awesome social network visualization. So if it looks like a duck, if it looks like a social network analysis, it's not social network analysis, it's actually NLP. I talked to them to make sure I understand which algorithm they use. Those are not ducks, those are geese. So what they used in NLP specifically, they used something that's called TF-IDF. It's term frequency inverse document frequency. So you have a lot of letters, okay? You have TF, DF, IDF. So you have your TF is the frequency counter for a term T in document D. You have your TF, the count of T in document D, divided by the number of words in D. In your document, you have your DF, the document frequency, is the count of occurrence of a document in the document set N the term appears in. You have the term T, you have the IDF. I'm sorry, I need to delete the first word in this last line. Inverse document frequency is the inverse of the frequency of the document in which in the document which measured the informality of the term T. Okay, a lot of letters. I'm sure maybe most of you first time encounter this is what was going on in your mind. Okay, so let's go about it in a different view. Okay, let's assume you have a word, which is your term, you have your book, which is your document, and you have your library. You have your document set, okay? So your word, and you have your book, and you have your library, okay? Lots of books in the library. Okay, so let's go back to the terms. So you have the TF. How many times a specific word appears in the book? You have your TF, okay? How many times a specific word appears in the book divided with how long the book is, okay? So it's like the weight. So it's not only how many, it depends on the how long the book is. So you have your TF, the document frequency. How many books in the library in which a specific word appears. In how many books in the library a specific words appear. You have your IDF, inverse document frequency, which means the frequency of the, which means the inverse frequency of the book, which measure the the informativity of the word. How much the specific word is important for understanding this book, okay? For example, if you have the letter, the word A, okay, or the word de, it will probably appears a lot of times, okay? So if you're just checking how much the word de appears in a book, it will probably be a lot of times. If you just measures how many times the word de appears in a book, no matter how long it will be, it will probably be a lot of times. Okay, so you check again, your word is there. Okay, if you see in how many books, okay, the library is only English. If you check all the books in the library, if they have the words there, it will probably appears a lot of times. So what you want to do is to see how much this specific word contribute for your understanding of the book, and it doesn't. So you have your IDF, which is you take the library, okay, all the words in the library, divided by how many books in the library a specific words appears in, okay? So I don't know, your word now is horses, and you check how many times these words appear in all the words in all the library, okay? If it's a very, very big library, it will be a very, very, very big number. Okay, so to address this problem, what you do is use a log. Okay, but this is also a problem if the word doesn't appear. Okay, if it's a new word, a specific word, a new term in a specific field, and it doesn't occur in the rest of the documents, in the rest of the library, it will be 0, and you cannot divide by 0. So what you do, you will add 1 for your equation. Okay, so eventually your TF-IDF, okay, you have in a collection of documents statistically measures how important a word is. Okay, so you have your TF. How many times a specific words appear in the book, and you multiply it by IDF. All the documents in the library divided by how many books in the library a specific words appears in, after taking into account a large library or a missing word, okay? There is a lot more to learn about NLP, but that is another story and shall be told another time. Thank you. Okay, we're done with this session. Any comments, any questions?
Thank you.
So,
So what do we need to understand from NLP?
NLP is neural language processing. If you have text, this is the way you computationally understand it. This is the field of data science that deals with text.
So we're going to use that in our tweets next week?
Partially because, again, there is a lot of things to learn.
Okay.
Any other questions?
Could you maybe summarize the key?
Sorry?
Could you maybe try to summarize the key takeaways from this session? Because we've talked about a lot of different things, and I'm not sure I managed to to grasp the key ideas of this session.
Okay,
What should I know at the end of this session?
Okay, sure. This is a good point to make. So what we did here today, we did an introduction to big data. Okay, we talked about a little bit of the data science process pipeline. Okay, there's a lot of, eventually it's some kind of a loop that you're going back and from understanding the domain and the question and the data and process it and and it's kind of a loop where the data is in the middle. Okay, so you have your data and you have your machine learning model. And in the machine learning, you have supervised, unsupervised, semi-supervised, and you have also reinforcement learning. Okay, so you have your supervised where you can where all your data is labeled, and then you can use classical machine learning, or you can use machine learning. You can use deep learning. Deep learning takes the algorithm one step further away from the programmer and one step closer to AI. In the middle, you have your black box, your hidden layer. And then we're talking about to a situation where you have maybe partially labeled data. Okay, so again, you have unlabeled data where you can use clustering or dimensionality reduction, and then you have partially labeled data. And you can use semi-supervised. And what you do when you're using semi-supervised is taking all of your data is like maybe 10% has labeled, and you train your model on that 10%, and then you predict the labels of the rest. Okay, this is called pseudo labeling. And then you have your active learner, your active learning model. And what you do is similar to supervised vision, supervised machine learning. And then what it does is things that it predicts pseudo labeling, but with low confidence, you give it back to the human labeler, okay, to the human labeling, so it can work better with better labeled data with more confidence in the model. Okay, so this was active learning. And then we had, we did a lot of stuff. And then we had reinforcement learning, where you don't have labels and you don't have data. All you have is actually the environment. And then you want to learn. Okay, you have the rules of the environment, and then you learn by trial and error and by reward and punishment. Okay, and then you put all of these things about the data science pipeline on the side, and we go to the beginning of the data science process. You have your data, and you need to understand it. Assuming that you have data, and it's not reinforcement learning, you need to understand your data, and how do you do it? This is what we talked about when your methods to understand your data, the types of variables that you have, their connection, and to maybe try to understand how many missing and outliers and maybe human errors that you have on your data, and all kind of histograms that are used for EDA. I know only by name, but you will have an access for a guide for it. And you had, we talked a little bit about what kind of measures you do, like bivariate visualization and multivariate, and maybe dimensionality reduction to understand your data. And then we talked about pre-processing your data. So you have your data, you understand it, and now you need to start preparing your data in order to put it in your model. So you need to clean it. And what is wrong kind of cleaning may cause your data, and what is the right kind of cleaning, and why is it important? Because your data analysis is only as good as your data. If you put garbage in your model, garbage goes out. And so we bad type of cleaning can tilt bad kind of cleaning can tilt the distribution, and it's more your conclusion of the data. And after this, we reached feature engineering. So you had your features and you talked about it in we connected it to maybe a health insurance equation and how different types of features may inflect on that equation, sorry. And how different type of features inflect on this equation. And then we talked about feature and influence, and I talked about a little bit about influence and how they used feature engineering to better understand social phenomena such as influence. And then we reached the topic of social network analysis. I'm sorry, it's not Corona. And then we used social network analysis also connected to influencers. And what they used, different kind of methods, like modularity and in-degree, and what is the network that it builds from points and lines, and specifically in data science. And we use nodes and edges. Okay, this is the social network analysis, and we talked about it connected to influencers, but it's not only connected to influencers or people or users. It's also connected to a computer network and connection between networks and connections between articles, and we view the tool that called Socrates Inside, and review the connections between authors and accordingly to what you search for articles. And then we understand their authors, their term graph, how to find out similar terms according to your field. And we talked a little bit about term frequency, inverse term frequency, TF-IDF, which actually measures how a specific term is important to your domain. And this is what we covered today.
Okay, thank you. And sorry for making you talk for so long.
No, it's okay. So I think that what we're going to do today, because I need to refresh a little bit and maybe drink some water, we will again put on a timer. Do you want 5 or 15 minutes? And
15, please.
What?
15, please.
15, okay. So I will stop sharing this string and I will put another a timer again. And now I will share the timer. Where is it? It's closed. Wait a minute. I will put a timer for 15 minutes. Okay, so here is the timer. We will see you back here in 15 minutes. I will try to call you. Is it working? Is it good for you when I'm calling you like a minute before to sit down?
Yes, it's great, Dina. It's okay.
I will see you back here.
We'll be back in about a minute if you want to come and sit down and join us. All of you are here. Everyone is back. Can I start?
I'm back. Can't speak for others.
I'm here.
Carl, you're there. Can I start?
Yeah, you can start.
Okay. So now we're going. We're starting our second session. This is a hands-on session where I will talk a lot and then you'll try whatever I say. Now I'm going to show you all kind of stuff in Python. Okay, we'll practice in collabs and you will get awesome notebooks to try. Everything is running and working. As the phrase said, it worked on my computer. But you shouldn't, I will come back to it later, but you shouldn't try and run all. And I will explain later why not. First of all, it will collapse. And second of all, it won't work because it's different variation of the same thing. Of course, there are other ways to do and write code in Python and more elegant way to do it using all kind of lambda expression, or if you know and understand pandas. I didn't do the elegant way. I did it in a way that people who don't understand pandas and don't know what is a lambda expression can also understand by seeing it as a for and I loop. So this session is a session that deals with the stuff that you do before you train. Before you train your model or your dragon. So why did I created this workshop? Well, about a year ago, I was offered a role of predictive modeling teaching assistant. So as the part of that role, I was supposed to choose the data set and prepare the notebooks. So I chose a huge Kaggle dataset with a lot of beautiful notebooks, but those notebooks didn't fit the course theory. So I needed to create new ones. So what are we going to talk about today? We're going to talk about the first steps of data preprocessing. Okay, we're going to talk to understanding our data.
Sorry to interrupt you. We're still seeing the timer. Are we supposed to see the presentation?
Yeah, wait, I will do it again. Sorry. Okay, so now you're seeing the slides? Okay.
Yes.
Excellent. Okay, so what we're going to talk about now is before you train. Now you understand why I use the word train your model or train your dragon. So again, I was offered the role as a predictive modeling teaching assistant. I chose a huge Kaggle datasets, a lot of beautiful notebooks and kernels, but it didn't fit the course theory, and then I needed to create new ones. And here where all of the problems are starting. So what we're going to do. So you have this data set, and then we need to understand how to, what you have in the data and how to handle it and what to do with it. What are we going to talk about? What is the beginning of the data science pipeline? We talked about it before. So we have the data science pipeline, and what we're going to talk about today is to understand the data and how to prepare it to the model. Let me tell you more. Allow me to introduce your data. So again, you have the classic data frame for supervised machine learning, where you have the future metrics and the target vector, the labels. We talked about it before, but we're going back to it again, because this is how our data set looks like. Why would you want to understand your data? Well, sometimes you want your model wouldn't address your data as it should be. Sometimes it will read categorical features, such as sometimes you're using queries like for one is married, 0 is single, 3 is divorced, 4 is a widow. Okay, so it's 0, 1, 2, 3, 4, and then you put it inside your model, and your model thinks it is dealing with numerical data. And it's not numerical, it's categorical. So you need to understand your data. And how are you going to do it? Okay, so you have your data, and you need to understand what type of data you have. What is it? So how are you going to do it? First, what do you need for that? You will need all kinds of packages of Python. So you have, first of all, the most important thing is to read the description of your data. You will have it in Kaggle competition, and you will have it also in real world problems if you're getting your data. And you have like a big CSV file. You will usually have with it a description of which each columns and what it means. The notebooks you will have, and the slides you will also receive it later. I want to prepare it in a CSV, as a PDF file, as well as the other one. I don't know if you know or try to use Google yesterday. They had a lot of problems, so I couldn't prepare the file as well build as I wanted to. I can share this slide. And I can share this presentation, and the notebooks you will have. You will have the link, and you will save them in your drive. So the most important thing is really read the description of your data. You will have it even in every real world problem. You will have your CSV or whatever the other data that you use, and you know each field, what it represents, what it means. And then you import all kind of Python packages. I don't know which one of you don't work with Pythons, and I don't really know that if every other language also built the same way, but Python, programming with Python, it's like working with packages. So you take all kind of packages and you use them, and you can write code with, I don't know, one line of code or 10 lines for image recognition, and it's very, very nice and intuitive language. So you have your NumPy for linear algebra, you have pandas for data processing. Those are the most important packages for data science. And then you have the matplotlib, which is data, and Seaborn, which is data visualization. And you have, again, from your NumPy, you have your statistics, and you have SciPy-Stats. This is also statistics, and we're going to use all of those in the notebooks. All of this you're going to have in the notebooks. Okay, so I talked to you about before about the EDA and visualization, that you're going to have an awesome recommended guide for it. This is it, if you want to use it. This is a connection to a Git repository from PyCon through 2017, I think. A very, very good one, covers pretty much everything. So EDA and visualization, you're gonna understand what kind of type is the feature, what is the type of the feature, and this is very, very critical. As I said, if you have like male and female in their in the data set, this feature is 0 and 1. When you put it inside and you start processing it, like missing the data or all kind of thing that you want to apply on your data, the code will address those features as numeric, because this is a 0 and a 1. The computer won't understand this is a categorical feature. So you need to understand the features, you need to understand their types. Data description is very, very important for this, okay? You need to view with your, to work with your description, okay? And to apply it on your data and to define it, okay? Because the computer wouldn't understand that 0 is a categorical feature. So you have your categorical feature that may appear as integer. Again, as I said, like your status, like a single married divorced widow, again, 0, 1, 2, 3, 4, it will appear as integer. And you need to make sure all of your features are defined correctly. I know that I'm taking the time with this one, okay, because it costs a lot of time and doing it again and again and again, with sweat and tears, and you need to really read this description and to apply it, because it wouldn't work. Okay, so why do we really need to understand that 0 and 1 is not numerical? Well, when you use all kind of methods to fill in the blanks, to fill in the missing data, and you use it like you want to use like mean or the average, or it makes no sense. Like, what is your data set have male and female. Okay, what is the middle? What is the mean of that? It doesn't mean anything. So you need to really define your categorical features. So how do you understand what you have in the data? So you have your data described. Okay, so what you have here is you have your numerical data. What this line of code does, it gives you your data description. Okay, describes your data. So you have all of your features. Okay, all of your it's right now it's the way your data looks like. So you have all of these columns. Is fraud, account, transaction, card, all kind of stuff. Okay, so you have your count, your mean, your standard deviation, you have your minimum, and you have your quarters, and you have your maximum, okay? So let's say we want to add it to this kind of a different view of this. Okay, so you have like in this specific data set, as you can see, you have 8 rows and 406 columns. So you wanted, this is something that you want to view differently. Okay, so what you do is transpose. You switch the way it looks like. So every column you had is now a row. And your new columns are count, mean, STD, and so on. Okay, this is your data described. This is your data now. Now, like the data that we're going to work with today is, this is, if you want to scan this QR code, it will bring you to the data set, to the competition itself. Is a fraud detection Kaggle competition data set. We're not working with the specific data set, okay? We're working with data set that is based on that data set, and it's different. I will explain. So the original data contains 2 tables. It had transactions and identity. Okay, and those tables are associated by the transactions. Your data contains both tables joined together according to the transaction ID and after some alternation. Okay, for example, the format of date and time, it's already set. And for more information, you have those links below. And I will, again, you will have access to everything, but if you scan the QR from before, you will also have all the information you need about this competition. Okay, so the first step, after reading your description, is defining the category features. Okay, so the category, again, so the category feature may appear as integers. You need to make sure all your features are defined correctly, because it makes no sense to make decision based on mean of a categorical feature. Okay, there are different types of way to handle a different type of data. If the data type is categorical, it's one way to handle it. If it's a numeric, integer, if it's float, if it's binary feature, different ways to handle your data. So let's define the category features. Now, everything I'm showing you today, there are a different way to do this. There is other way to define category features. But specifically in our case, none of the other ways to do this didn't work. The only thing that did work is to define every one of those columns as type string. This is the only way that worked in this specific case. Okay, so there are other way to do it. Okay, included applying it to apply it and calling those are objects and all kind of stuff. But this is the only way that works in this case. Okay, so sometimes in different sets of data, you need to again Google it and find out many different ways to encounter a problem and try to solve it. And initially one of the ways are supposed to work, and if you create it, and sometimes it doesn't, and you need to combine methods and be creative. So handling time delta. So you have in the original data, you have a transaction time delta. Okay, it was given from a reference data time. Okay, there was a specific data point where they started measuring the data. Okay, and it wasn't an actual timestamp. So the data that you are working on is a data with a timestamp that we added. Okay, it's not the original transaction DT. It's another timestamp. Okay, so what we did is important date and time. And then we created more columns and more features such as date, days of the week, hours, days and month. And then we dropped the original transaction DT. Now, as you said, sorry?
I'm sorry for stopping you. I'm a little confused. The original time delta field was in relation to some fixed point, or was it the time frame of the transaction, like, I don't know, time between click and some other event?
Okay, so you see the date in the beginning, the start date?
Yes.
Okay, I don't know if you ever encounter a Kaggle competition. There is a discussion page where you can say where you can ask questions the managers of the competition. So in one of the discussion over there, when they talked about this specific field of the data, they told to address the date as this date as the starting point. Okay, so you have the start point, and you have only the delta from this specific date.
Okay, so to reach an actual date, you would need to add
you need to calculate
add this delta to the time, to the original time.
So you have the start date and you have the delta. So to calculate the real time, you need to take the start date and to add the delta to that start date. And then to calculate how much time passes from the original start date until the point of your, until the time point of your specific transaction. Is it clear, or do you understand?
I think so. I think I understand. So instead of, like, they could have used, if they had used like epoch time stamp, we would have to add January 1st, 1970 to convert to the actual human readable timestamp and get that
exactly.
They just used 1st of December 2017.
Exactly.
So we are trying here to extract features that describe, in a way, capture the seasonality of the data, right? Because if we would use actual date as a feature, we would probably end up like not fitting very well at all to things that happen later in the future.
Right. Because right now, when you're this specifically is fraud. So this, when you're taking your delta and converting into a real time, you can see in what seasons of the year there are more frauds, in what time of the day, in what time of the year.
Okay, like maybe there is more fraud on, I don't know, the 1st of each month.
Yeah, exactly. Maybe there are more fraud at night. Maybe around Christmas there are more frauds or something.
Okay. All right. Thank you.
Okay. So I show you what I did. Okay. And this is your data set itself as those features. Okay, you have the weekdays, the hours, the days, the month. Okay, and you don't have the transaction DT because you don't have nothing to do with it. Okay, so your data, the data that you're having and working on is a data that is based on the competition, but it's a little bit with a little bit adjustments. Okay, I'm just showing you the adjustment that you have. Okay, another thing that is important in your data set is understanding the cardinality. Cardinality is you're trying to understand the uniqueness of the data values in a column. For example, if you have a lot of data points, you want to understand how many let's go back to the example of singles, married, divorced, etc. So you want to understand how many are there. So there are, I don't know, there are single, married, divorced, and widow. So you have four. You have four features, unique features. You have 4 unique values in your column. And you want to understand how many values you have for each. Okay, so this is what cardinality is for, and those codes. Okay, so reducing cardinality. Why and how should we do it? That. Okay, so you saw the n unique. Okay, it counts for how many different data points how many different values you have in a specific feature. Okay, in a specific value. So we take a device name. Okay, so you want to know and understand the device info, okay, to understand which device names you have over there. And then, okay, so here you have the n unique, okay, you have a lot of different values. Okay, let's print them. Let's see who they are. So here you see here you see n unique, and you see the count, and here you see unique, and where it prints which different types of values you have. Okay, so you have Samsung SM, and you have another one SM, as I put on a color in it, and you have another, but those are different. So you have SM, Samsung SM, and each one of them, you see they are similar. Okay, so similar that are pretty much, they can be the same. So why not put them together? Why not joining them? I mean, those are Samsung. This is the machine type. So what difference does it make? So we can reduce the cardinality. Okay, so how do we do it? Okay, so we take those are strings, and you see string in upper, or you can do lower. What it does is takes all of the letters and put it in an uppercase, or lower and put it in a lower case, and then you take and you split it. Okay, you split it into words. And then what you do is you find a string that contains SM, and you call it Samsung, and you find a string that contains Samsung, and all kind of this combination, okay? And then you combine them together. SM, Samsung, GT, all of those are Samsung. Moto G and Moto, all of them are Motorola. You see Howie, ALE, and you see L, all of those are Howie. Okay, and what you do is combine them together. And this way, we can combine the cardinality from almost by half, more than half. Okay, this is what it's used. So right now, if you're trying to understand which kind of device has more fraud, when you had many different values, it's very difficult to understand some kind of a trend of a specific value. So now you reduced the cardinality for more than half, and now your data set is set to this, okay? So your data set contains this amount of features of unique values, okay? Now we can even reduce cardinality even more. And what we do is all of those that are unique values and have maybe, this is a huge data set, it's like have 500,000 points of data, okay? So we will take all of those that occurs less than 200 times, it can be any other value, okay? We make all of those be others, okay? But by doing this, we reduce the cardinality to 13. I didn't do this in your data. Can anyone tell me what are the pros and cons for doing this? What do you think? Should we do that?
You lose data, you lose information, basically. I mean, maybe there's information in the device name that you put in the others, and it can you can conclude something from the name, like, I don't know, all Chinese companies, all Chinese device companies, or for example. But once you put, I don't know, OnePlus inside others, then you lose this information. Mm-hmm. So it depends on your question, I guess.
Yeah, that's right. Another thing that you maybe want to, another thing that is problematic about it, that what if the low cardinality is what is predictive of a fraud. But then you can answer, well, it's, yeah, it has low cardinality, but all of them are together, and everyone that has low is unique. Okay, it's something that doesn't appears a lot of times in the in the data set. Maybe this is something that's predictive, the fact that it's not unique. But as you said, if it's we want to see a specific company, we lose that data. So this is, in your data set, you have that before, the 600 and something when we reduce to similarities, but we didn't do this to make to all the unique to put them together as others.
Can I ask, when did you use this type of reducing cardinality? I mean,
I used this in this specific data set for this specific course in order to understand the data.
But did you find yourself doing it in other types of, I mean, is there a type of data that you want to reduce cardinality this way, to put in others? I mean, I can think of a case that you feel okay with losing this information.
Well, as I said, are pretty much similar. I mean, if there is different way for the same thing, it's supposed to be with together with domain understanding. So if there is a lot of different things, a lot of different names, again, most of your data is based on data sets like, I don't know, like medical data. So you have all kind of ways they are writing the same thing. Like,
yeah, no, I mean specifically about the case of putting everything that appears below 200 times as other.
I didn't use it actually, but I saw that people are doing it. To just, you know, this is on the side, we don't really need it. Maybe what you want to generalize your model to avoid overfitting, you will use it. But again, it's not, as you said, it's not the best thing you do. I just want to show you that you can reduce cardinality even more, a lot more, sure. So now I want to show you some cool trick. Again, everything I'm sharing with you is usually stuff that I didn't find an answer. I didn't find a tutorial on how to do it, and this is why I create one. So this is a unique trick. I'm taking you back to the data described from before and the transpose, and as you've seen. So there is all kind of data okay, your numerical data, and you can add to the original one and the way it looked from the beginning. I will show you it in a minute once more. Okay, and then you add to that table a lot of features. So you can you have your feature. I don't know if you remember. It's like data described as like your sum, your standard deviation, your mean, your quarters, minimum and maximum, and then what you can do is add to that table the correlation of the feature to the target. You can add to it the data types, how much missing values you have, the cardinality of that specific feature, the skew, which measures if it has like a skew, like imagine distribution, and if it has a skew on the side. And you have this
skew?
It's like a tail for distribution. Imagine the curve, a bell curve. So it's the side. You understand?
So it measures whether the distribution is more one-sided?
What it measures, if it has a distribution that looks like having a tail.
Okay.
Okay, and then it measures the z-score and the p-value. Okay, this is the z-score and p-value of the skew set is for trying to understand if it's any way a normal distribution and how if it's related to it. Okay, and then you take those and you put it inside if a new feature is the z-score and the p-value. And the ketosis, it measures also, it's connected to the distribution, and it measures the distribution of the feature. Okay, and we want to understand the distribution of a feature because sometimes we will want to process your feature, okay, to fill in missing values, to deal with the outliers according to the distribution of the specific value. Okay, and now I'm going to show you. Oh, and you will have also a little bit more information about what I just said about filling according to the distribution in a bit. Okay, so we have the distribution. Okay, we're having the data described, and as I've seen before, this is the way it looks like. Okay, so you have your data described, and then you should transpose it, and you have the count, mean, so on until the max, and then you put on all those additional columns to the table. Again, this is what I showed you before that we're going to add to your described table, and then it will look like something like this. Okay. So you have the skewness over here. It's supposed to be the z-score. It went to the side. Okay, so you have your count and all. If it's correlated with the target, and you see the data types and how many missing values you have, cardinality and the skew, and this is supposed to be skew and z-score, p-value, outliers, and ketosis, which also shows the distribution of your data. This is for you. Any questions about what we had until now? Here we have the link for the first notebook, but in the end you have the links for both, and I will share them with you. Okay, would you like us to continue on the next session, and then you will have the two notebooks and you can play? Sure, okay. So now we learn about the data, you know what data you have, you understand it, and now what we're going to do is to handle it. Okay, now we will cover what we're going to do with missing data. transformation of the data. This is what we're talking about, the distribution of the data, and outliers. Again, as I said before, I will introduce you a couple of methods to do that. I will talk about the pros and cons. And there are probably other ways to do it. There are other ways to write the code. This specific code is supposed to be without unique ways to write things in pandas. It's not a pandas way, elegant way to do it. It's not so much with lambda expressions. It's more intuitive with loops, so you would understand. Anything I said, there are other ways that anything that can be done can be understood, and you feel free to ask any questions you like. So, missing data. This is the visualization of our data set. Okay, see how many missing data you have. As you can see.
I'm sorry, what are we seeing?
This is the visualization.
In the frame. Like, what is in this graph?
Yeah. Okay. So what you see all the small number on the bottom.
Yes.
There are all of the feature.
Okay. So that's the feature identity. That's the feature name. At the
downstairs is the feature's name, and you see how much missing rate, how much missing data you have. So what
they're ordered by the missing rate.
Yes. So you see, okay, you see, you can see my pointer? Yes, right?
Yes.
Okay, so you see here, this is about 80% missing.
80% missing.
80% missing data, and you can see that this is more than half of your features. More than half of your feature has more than 80% missing data. Okay, so this is a lot of missing data. I'm not talking about it. Sorry?
How do we know that? How did we create this graph?
I think you have it in your notebook. It's a few lines of code. It counts how many missing you have, and then you plot it into a graph. But you also have it in the data that described. You can see how much missing points you have. I don't remember if it's by percentage or by count. Wait, we can look. You have missing. Yeah, you have. You see, 99% is missing.
What does that mean? I need the context.
Okay, so you have this. You have a table of features. Okay, so you have you have rows of transactions. Okay, and you have columns. Columns is your features. Like one column is the date of the transaction. The other one is the ID of the transaction. The other one is the credit card type. You're with me?
Yeah.
Okay. So right now what you're seeing below is the features. It's the columns. Okay. How much is columns? For each columns, how many transactions? Okay. How many rows are missing as missing values? And this is with percentage.
Okay, now I get it.
Okay.
Thank you.
Thank you. Okay, so we have a lot of missing data, and I don't remember.
For that one.
And you will have your notebook. This is just a visualization of the missing data. You will have it. I'm just giving you the intuition and to understanding why you need to fill in the missing data or to do something with the missing data. Because real data, most of the real data is missing. If you have a lot of feature, a lot of like maybe you have a questionnaire, okay? You can either fill in the blanks or not, okay? And each one of the blanks is a column in a data set. Okay, and each one of a questionnaire, it's a row. Not everybody filling all of the missing blanks. So we'll have missing points in a specific column. Let's say this is an Excel spreadsheet. Okay, Excel spreadsheet. You have a lot of rows. You have a lot of columns. Okay, some cells are having data. You want to ask a question? Okay, so you have, we have a lot of missing data, okay, and we need to do something about it, okay? We cannot apply a model on a missing data. Okay, so what are methods that we can use to miss that data points? Okay, so you have, you can drop them. Let's say everything that has more than 80% missing data, drop it. You can just, knowing it's missing, you can flag it. You can add another cell, missing data, true or false. You can fill it with nuns or with zeros. You can do a forward or backfill. We will cover all of those, okay? You can fill the nodes with mode or min. You can fill the nulls by the distribution, and you can handle the nulls with interpolate. And now we'll cover each and every one, and I will explain it. Okay, don't worry about the code, you will have access. I just want you to understand. You understand the concept that you're having, that most of your data is missing, and you need to do something about it. Right now, I want to explain to you methods and the consequences of what you're choosing to use, okay? So one way is dropping your missing data, okay? You can drop all, you can drop your columns, you can drop your rows, you can drop rows with at least two, for example, 2 missing values or whatever it is you want. You can drop, you can define specific columns where you want to drop if there are missing values at. You can, and you can, and this is the way you do it, okay? You find out what is your missing rate, okay? You want to understand how much percentage is missing, and then accordingly you decide on what to keep and what to lose. For example, okay, so you will want to keep only those that has more than, you want to drop all of those that has more than 80% missing data, for example, okay? But then what happens? You use your data. You use all kind of columns. So you can also you can use a filter, initial filtering by criteria. So you apply it on those that maybe has a low correlation with the target, and also that has a lot of missing point. Okay, so you're dropping, what you do is take all of those that has a low correlation with the target, who is not predictive, and then you're combining them with those who has a lot of missing data. Okay, you use intersection, and then you combine them together. Okay, those that has low correlation and both has a very a lot of missing data points, a lot of missing values, and those are the ones that you want to drop. Okay, you won't drop everything. You will drop only those that are has low correlation with the target, that are less predictive. So you won't just drop all of your missing data because most of your data is missing. Okay, you filter your data points, you're missing data, but then again, you still have missing data point. What do you do? So before you drop, as I said before, let's go back to the cleaning. So you have your data set of, let's say, housing prices, and then you have missing values for the houses that doesn't have a pool. Or for example, you have a feature that is the size of a pool, okay, pool size, and for a house that says that it doesn't have a pool, you will have missing values. Now, if you just lose those, drop those missing data points, those rows, okay, or you will tilt your distribution. This is an important variable for understanding the prediction of the housing prices. So what you do is flag it. Okay, you can just flag it. Let's say is none. We multiply our data set and we combine it, and for every feature you now have a new column with the name of the column, and for example ID is none. Okay, what it does and why you shouldn't do it. Okay, because it multiply your data set. So if right now you had a data set with 400 features, now you have a data set that contains 800 features and 500,000 of rows. Okay, this is a huge data set, and if you will try to use it and run it inside your free Colab platform, your notebook will crash. So a way to do it is just, well, if it's missing, let's just write none, or and if it's numeric, let's fill with 0. So you're doing this, and why it's not good? Or at least it's okay, but well, why it's not the best thing to do? Well, sometimes, as I said, 0, for example, is a number. 0 is one of the values that already exist in your numerical column. So if you're just using a fill with 0, it will tilt your distribution. So what you can do is use your distribution and your statistical measures and fill the nuns with that. We take the mean and we take the mode and you fill it. If you have an object, you fill it with a mode. Which one of the categorical values is the most common? If you have an integer, you will fill it with min, but a round number, because you don't want to put now in this column, you don't want to put in a float. And if you have a float, you will again put on your min. Which one is is the most common? Again, if you imagine for a minute a bell curve, okay, and most of your data is missing, okay. Right now, if you can see, you can imagine all of those, like in Instagram, a bar chart. The bar chart for this specific value will skyrocket. If you have like 80% or 70%, it will be the longest bar in your data. Not a perfect solution. So you have a forward fill and a backward fill. You have it in your notebooks as well. So what it does, if you have like a column, what it takes, a forward fill, if you have a missing value, it takes the next one, and if it filled accordingly to the most closest one. If you have a backfill, it takes the value from before and fill it. Okay, so this one a little bit, it's way more random than filling with a mode or the min. Another way is to take into account the distribution, what we used before, the skew, to see the skew and the specific distribution of the variables that you have, the values. So this is a little bit more complex algorithm to really identify the type of the type of distribution and how to fill it accordingly, and to use the distribution to fill in the nulls. Connected, if you have integers, you have your deviation, and if you have your float, you will use maybe Gaussian distribution of it. And you have it also in another way to fill in the data and the distribution. You also have this in your notebooks. Now let's look a bit about a wider look on missing data. Okay, so we're looking at an income report, and the salary column is missing data. Okay, so you have the salary column, and you don't know how much this man is missing. If you're just looking at the salary and use anything that I described until now, okay, it's not completely true for the specific value for this specific column. Because salary is also affected by the education level. And agree, it doesn't want to earn as much as PhD maybe. Maybe the field is also important for this value. Okay, what is the field of the education, and what is the his profession? Okay, and so on. What is the sex? Unfortunately, there is still a gap in the numbers. Or in location. Where is he from? So another way to handle nulls is by interpolate. What you do is to use some kind of regression connected to every other feature in your data set. Okay. Also, you have it in your notebook, and you can play with it and understand how it works. Okay, this is the way it calls. You have it in your notebooks. Okay, so you have all your feature, and you're missing data points, and you really need to avoid overfitting your model. You need to generalize it, as I said before in the previous session. And this is very, very important, and it's something to avoid. So now what we're doing to avoid this overfitting is data transformation. Okay, you have your data and you want to transform it in order to generalize your model and your data. So you maybe used, first of all, you want to see if they has a skew. Okay, so you want to check if they have a skew. Okay. So you're checking it, okay, and then there is a skew or there isn't a skew, okay? Does it has like a tail? And then we want to see if they have a positive tail, and then to transform it. And then you want to see if it has a negative tail, and this is a different way to transpose it also, to transform it. Okay, again, you have everything here.
How does this normalization help us avoid overfitting?
Because it takes the edges from the sides, and your data itself, it transforms it to more normalize it. Okay, and then you can, the model, it avoids, it's instead of maybe another way to adjust to the outliers, you don't address all the points in the tail. Okay, you don't if you have the if you have an ending point, okay, a unique occurrence of something, you don't take it into account. You generalize your model. So next time when you have new data, it will it can be it will work on that also.
Okay.
Okay, so you have your transformation data. Okay, this is one way to do a transformation, to check if it has a tail and in which size the tail is, and the way and then to address it. Okay, to transform it, to cut and snip those tails. Okay, and another way is to maybe look at your outliers. So you have your distribution of the data. Okay, it doesn't necessarily mean it's a curve or a bell curve or any curve at all. Okay, and what it does, it remove from the edges or move the edges. Okay, so you can remove the edges and you can move the edges. Again, it's this is what we do this in order to not overfit our model. So if we're training our model in a specific data, when you test it, you will have a higher validation and higher accuracy of your training set, your test set. So before you go on to the notebooks and just perform run all, okay, you need to wait a minute, okay? Because you don't really need to do it, okay? No, you don't need to do all of this, okay? You just need to understand, and you need to understand that what you choose, you need to understand and understand that why we did all of this. You need to know all of this because you need to understand that what you choose and what you do has consequences. And this is why you need to choose wisely what you do and how you address your data and the way you handle your missing data or your outliers or your transformation. Everything has consequences. It can transform your data and it can tilt your distribution and eventually your accuracy of your model. So you really need to understand that it's very, very easy to Google it and find something that works and just apply it and to do run all. But there are different ways and different methods to do everything. And you need to understand what you are doing and how it affects your data set. And if you take a data and you torture it enough, it will confess. Okay? So this is something that you really, really need to take from this. And thank you. And if there is any question, I will go back. And if there isn't, now you start. Sorry?
Can I ask a question?
Sure, of course.
About data transformation. Can you just decide that you do, I don't know, a log transformation or whatever you choose on one specific column, or do you have to do it on all columns or whatever?
You can, I think that you, first of all, whatever you do, you on the trainings on your data, okay? The way that what you implement on your data set, okay, there are stuff that you need to do both on your train and your test set, okay? For example, if it's the way you address a specific column, like if it's numeric or if it's numeric or non-numeric, okay? So you need to apply both. The way you fill in your missing data, you need to apply on both, okay? Whatever you do between your test and your data set, you need to apply on both, okay? This is the first thing. The other thing is that you can address on a specific column something, but then again, you need to do it also on the test set, on the same column.
Yeah, but I mean, within the specific table, within the specific data frame, I can do data transformation only on one column, on a specific column that I think it needs to be transformed.
Yes, but I don't know if you notice on the set, there is also a condition inside it. It needs to, it doesn't work on anything. It's supposed to have a higher cardinality than, I think, 8 or 10. It's supposed to have a specific kind of cardinality. It says also a lot of condition. So even if you choose specific specific columns to apply it on, it won't apply on everyone because of the equation itself. It will return infinity or something like that. Okay, but it's needed a lot of domain understanding to really choose which one to apply and which you don't apply. But other than that, you can take it to understand on which kind of columns you can apply it on. Okay, I think you also have prints to see in which columns it can be applied on, and then you can choose from them. Okay, so now I'm gonna stop the sharing, and I will, if there isn't any more questions, and I will give you the notebooks where you can play, okay, in the chat. Those are the notebooks. I will send it also inside the WhatsApp group. So now you have the links. Again, don't run all, okay? Because if you already filled the missing values, you cannot apply a different way to fill in it because you won't have missing values. If you apply a fill in missing data with zeros, you won't have after that a missing data, or missing values. You will have, sure, I will have the slides from those sessions. I don't know if you know, but yesterday there was a little bit of problem with Google, so I couldn't, I didn't get to preparing you the same PDF as I did for the first one. Okay, this is the slides. You see the slides? I will share it also inside the WhatsApp group. So you have the slides and you have the notebooks from this session. And I will share with you the slides of the first session, so you can press on the link over there. This is the first intro to and I will share a screen for a minute of Colab. I don't know if you know how it works. You need to save a copy to your drive, or else you can also work in playground mode. But you need to save it on your drive. And I will share a screen for a minute to show you something about Colab. Where is it? Okay, this is Colab. Very nice to meet you. And there are stuff that you shouldn't run, as you see. Don't run everything. Beside it, if you're feeling missing values in one way, you won't have any more missing values to fill. If you run all, it might crash. Okay, so this is a Colab. Okay, here you have connect. You can connect to local host runtime, local hosted runtime, your runtime, manage session. Okay. Here you can view what files of Colab are working and terminate them. Okay, if you have many, you can see how much RAM it uses. Okay, if you have a few like this over here, and you might want to terminate them to, so you have more computing power. Okay, in runtime, again, you can, if you're standing on a specific cell, you can run before and you can run after. You can choose a couple of cells and to run only them. You can, all of those, okay, interrupt, restart and run all, don't do that either, don't run all. You can reset runtime, which means that you have it crashes and it's working slow, you should use it. Okay, and this is something very, very important to know about Colab. Okay, Google are very kind. Okay, and it gives you, if it's on none, it means that it works on your computer. Other way, Google is very kind. They give you GPU. Okay, and they save it, and then you can see. Wait, you can see. Okay, you can see that they're giving you 12 gig RAM and disk of 60 giga also. This is from Google, their GPU. The TPU is is very similar to the GPU. Okay, but this is a TPU is connected to transformers, to the TensorFlow way of saving. If you know, if you heard about TensorFlow, and it's more connected to data of pictures, of images. But if it's working slow and it doesn't work for you, you can just play with those runtimes. And wait.
Is there a CSV file of the data, or do you need to download it from the Kaggle and to register to the?
Okay, so you see here loading the data set.
Mm-hmm.
Oh, you see, this is just load. I think that Guy Smoilov put it on in his
drive.
Sorry.
In his drive.
In his Amazon bucket or something, and those are his contribution to this notebook. So you can just run it, and in a few seconds it will be on your notebook without downloading anything.
Great.
Yeah, because again, it's just working very, very slow to loading the data. But another thing that you want to know is, you see here on my screen, you have connect to drive. Those rows that that I colored. So you have this is the way you connect to your drive. Okay, you can save to drive. This is some kind of you have your data frame of transaction or whatever, you load it to CSV. This is a standard way to do it. And this is the way you write where is your data set. Okay, you have your G Drive, Google Drive, My Drive, and Colab notebooks. Hopefully that your Google Drive and everything is in English, because in Hebrew it doesn't work. I don't know in other languages, like Cyrillic languages, if it would work. I'm assuming it will be a little bit more similar to the problems that they have in Hebrew. Okay, but this is the way you save it to Drive. Okay, if you want to compress it, you can use this expression. Okay, this expression is so you can compress it. Okay, and if you want to read it, this is the standard way to do it. You have the name of the data frames, where you're saving it from, PD read from CSV, your Google Drive, specifically it's in the Colab notebooks. You have the point of CSV, the way you call it, whatever name you decide to call it, and then you call it with the compression, in case you use this one when you save it. Okay, this is the way to do it. And now you can play with your data. I will stop sharing the screen, so if any one of you will, Gal, can they share the screen if anybody has a problem?
I'm not familiar with the Colab notebooks. It just runs in your drive? Do you need to like install something?
No installation. It's a perfect tool for teaching. No Jupyter notebooks. It looks the same if you, I don't know if you're familiar with, but there is no installation. You don't need to worry about versions and that everyone will have the same version and everything. It will just run on your drive. You will probably, if you open my file, you will probably have here a playground mode. So you can just do whatever it is you want without saving. But if you save a copy to your drive, it's your Colab now. And I think that also with me in a WhatsApp group that called Data Science managed by Morag Shiloh. And one of them suggests the expression of Colab. I really, really like Colab. It's a great, great tool. It's easy to work with, really. And I don't know if you're working with Git or writing, I don't know, writing on Medium or stuff. For saving on Git, it's you just saving a copy in Git or saving a copy as GitHub Gist, and then you can embed it inside your I don't know, inside your Medium or your technical blog post or whatever. I really, really love it. And you can download it as Pi if you want to use it inside of your PyCharm or Spider or whatever. And you can do everything. I really, really like it. So this is it. This is the first one, and I can open the second one, and you can play with it. Let me see where the end is. This is the second notebook. Again, the load is the complementary of Guy Smilov. Okay, and then at the end of this session, on the second notebook, the before you train 2, there is something extra. Okay, what you have here is your data set. Do you see you have data is fraud and data is fraud 0 and 1. The data is labeled 0 and 1 if it's fraud or not fraud. Okay, this is an unbalanced data set. Okay, this is something extra. So there is about 15 minutes more to what we scheduled today. I know that you didn't have a lot of time to play with it with your notebooks, but I think that you're having the notebooks and everything is working. Hi. And everything is working, and you can play with it and understand better and by trial and error of everything I covered today. Most of I've been in a lot of meetups before, and this is, I know that we didn't get to the point of fit and split and everything that usually they're in meetups. And this is kind of the point, because most of the meetups you have like this perfect data set or whatever, and then you have this like okay, let's put it into skitlearn and put and we split it and fit it and let's put it inside a model. This is most meetups that I've been at. And this is something that was missing for me, and this is why I decided to create a session about the initial parts, the dirty parts of the data science process. I hope you enjoy it. I hope you will have fun with the notebooks and to play with them. And if you want, we can discuss a little bit about what are we going to do if there is an unbalanced data set. What can we do about it? I mean, if there is, I don't know, like you have your data and you have like 93% of your data is not fraud. Okay, so if you have a model that you're that is predicting every time that it's not a fraud, it will still be right at 93%. This will be the accuracy of your model. So what do we do about it? What do you think?
We use a different metrics.
What will you do?
Like the percentage of correctly identified fraud transactions, but with some deviation to the number of correctly identified real non-fraud transactions, because I can identify everything as fraud and get a very bad accuracy, but I would still get all of the fraud transactions correct.
Mm-hmm. Dikla, do you want to add to the discussion?
Yeah, maybe TPR and TNR. I think that's the most useful.
I don't really hear you. Sorry, I will try.
TPR and TNR. No.
Mm-hmm. There is all kind of metrics to evaluate, all kind of different methods like accuracy and F1 score and area under the curve and precision and recall. That's right. And wouldn't we do something about the data? What do you think about the data? Is there anything to do about the data itself?
we can either undersample the majority class or use some kind of data augmentation for the minority class.
Mm-hmm. So what you're saying that we can maybe
balance the data in a way.
Sorry?
Balance the data, or at least change the change. Oh, never mind.
We can maybe, if you have a lot of, I don't know if you remember, but there's like there's still a lot of, if you're just taking the points that are fraud, there are like 20-something thousand cases. Okay, so you have 20,000 data points that are fraud. Okay, and if you're taking like 20,000 from the rest of the data, that you take the similar amount of points that are not fraud. Okay, so you're creating synthetically a balance data set, a very small one. Okay, this is also problematic. Can you maybe think about why it's problematic? Do you want to talk about it?
First, a smaller data set usually may lead to overfitting, or let's say the other way around, the largest data set would help us overcome overfitting. Besides that, how do you select the 20,000 from the majority class? It should correctly represent the majority class. So there are many aspects to take under consideration here.
That's right. Another way to handle with the dataset itself is to use something that's called SMOT.
Yes.
And what the SMOT does, it synthetically generates a larger representation of the lowest category. It multiplies it. And
yes, in their article, they say that the combination of exactly what you've just described with let's say a little bit of undersampling of the majority class provided them the best results.
Mm-hmm.
But as far as I know, it's not good to take it to the extreme. So let's say if the unbalanced data is like, let's say 1% of the data or even less, then you shouldn't bring it to the 50-50%. It should be, let's say, maybe 10-20% versus 80%. Mm-hmm. So this is my note on that.
Okay, can you maybe, okay, so now we have the unbalanced data set. Okay, so you have a problem that even if it predicts everything is not fraud, it has a high level of accuracy. Can anybody maybe think of another problem with an unbalanced data set?
You're not referring at the moment to the metrics as
No, I'm not. I'm referring to the model itself. What can be problematic when you're trying to put it inside the model itself? What can be problematic about it? So let's say you have the data set and all of it, it's 0 and 1 for fraud and not fraud. Okay, and then you do a split and you split it into this test and
okay, in that case, you have to split it in a stratified way, in the sense that it's important that you retain the percentage of the positive and negative samples in the training and the test set as well. So, because when it's unbalanced, it's you might fall into the case where all the small amount of negative samples will fall only to your test set or only to your training set. So your model wouldn't learn anything or wouldn't be able to predict anything in that case. So
that's right. That's right, that is the case. Okay, so I hope you enjoy your session today with me. And I know it was, even though that I tried to convey a lot of information and a lot of stuff, that you're taking something with you besides the slides and the notebooks. And that's it. Anybody wants to tell me how it was and what to improve maybe?
I think it was great. The part that I think that where I'm a little bit lost is with data visualization. Like, you get a data set, how do you deduce all of these rules that the data follows? How do you see it? I mean, yeah, you know the field, but apart from that, what do you use to look at the data and decide, like, what kind of methods are better to complete the missing value? Like, where do you get the logic of the data from? Because we didn't do that, and it's really a gap. It's really bothering me.
Okay, so I gave you the EDA tutorial. It's in the second slides. Okay, it's connected to a Git repository that explains exactly which kind of variable, which type of variables you plot with and you validate with each other types, and how to visualize it, to see it. When you have, I don't know, here we have 400 features. To plot all of them is a lot, and you probably won't try to visualize everything. You maybe try to visualize section by section, and if it's again, it depends on if you want to see a specific variable and how it looks like. If you want to plot two variables and to see their connection and if they're complementary, and if you want to see if they are connected, and if you want to see if a feature is connected and correlates to the prediction, to the target. Okay, if a specific one, it helps your prediction of it's just not that important.
So what's like the, say, rules of thumb when you're entering a new field, a new data set, and you want to just, get a measure of what's going on?
If you want the plotting and understanding the variable, it's statistics, descriptive statistics. Okay, so you need to understand, to familiarize with your variables in that kind of aspects. Okay, to see the mode and the mean and the minimum and the maximum, and how does it look like how many unique values you have, and which one are they, and how many for each kind of unique values, how many values does he have, how many value counts he has.
Maybe I wish that we do more of that. That would help. because I understand what you're saying, but it's like I'm having trouble.
Yeah, but this is something that cannot be conveyed not in 2 hours, and I think I'm not sure it can be conveyed in 4 hours. It's a fully syllabus course of a university to understand descriptive statistics.
Okay, fair enough.
But you have everything. You can go deep inside every theory and every mathematics and every statistic about everything. Okay, or you can just, I can give you just what to look for, and then you can see where to go in deep and how to apply it, because I can, specifically about myself, I learned a lot of stuff. Do I remember it every time I go to a data set? No, I probably Google it and I try to apply it and it doesn't work and I try something else and figure it out, and yes, this is connected to this one, and this, you understand what I'm saying? I don't know what you learned, but I'm pretty sure that after you've taken an exam or a few weeks later, you don't remember everything. So I can.
No, I did learn some statistics in university. It's not that I'm clueless. It's more that when you're accessing a data, like a huge data set, what are like good starting steps, say, just to start understanding what's going on and who's against who and where is.
So a good start would be that, specifically in Python and what I showed you, a good start, if it's a very, very, very big data set, is not plotting it, is putting it inside a table to understand it. Like what is the data, the specific table that I gave you how to do. You know, the minimum, the maximum is the data describes. It's very a good start. But to add for it, how many outliers and how many missing data and the amount of uniques inside a data set, it's a very, very good place to start when you are dealing with a big data set. Because if you have, again, if you have 400 features, if you have a table with 400 columns, and you want to plot for each one of the columns a graph, you will be lost between all of those graphs.
I see what you mean. Okay, thanks.
Sure. Well, I will release you now. So have a great, great weekend. And thank you for being here. And I will see you next session. Make sure you have a Twitter account. It doesn't have to be a real one. You won't post anything through your real Twitter. So even if it is your real one, you don't need to worry about it. Okay, we just will transform your account into a developer account, and we'll use its credential in order to mine the Twitter data. Okay, so we won't post any embarrassing tweets in your behalf. So this is it. I hope you like it.
Thank you, Dina.
Thank you very much.
Thank you.
Bye.
Thank you, Dina. See you next Friday, everyone.
Bye-bye.
Bye-bye.
Thank you. It was very informative.
Thank you.